and introduce our keynote speaker, Dr. Sean Boyle. He's going to talk to us about conservation in a human-dominated landscape. Sean did his undergraduate degree at Brock University and then did his PhD at Laurentian, working on road ecology at Presqu'île Provincial Park. He then went and did a postdoctoral fellowship at MUN at Memorial University in Newfoundland with Eric Vanderwall. He's currently a postdoctoral fellow here at Carleton. And he started in January, and he's already gone because Sean is founding his very own herp lab in I know it's also going to have moose, but it's a herp lab, right? It's a herp lab, right? At the Grenfell campus of Memorial University, starting in January 2024. If you don't know where the Grenfell campus is, it is in beautiful Corner Brook, Newfoundland. And if you are interested in future research opportunities with Sean, he would love to talk to you later on after he's given his keynote.
Awesome. So who's having a good CHS? Yeah, it's been great. Great talks, excellent talks, lots of fun. The banquet was great last night. Yeah, I'm having a lot of fun, and I'm glad everyone else is as well. So before I get into my talk today, I just want to take a second to acknowledge that where we're gathering today is the traditional land and territories, and unceded territory of the Algonquin Nation. And the research that I'm going to be discussing has occurred on diverse Cree, OG Cree, Huron Wendat, Anishinaabe peoples' territories, as well as the homeland of the Métis. And I want to take it an extra step and say that part of our responsibility gathering here today and learning and sharing together is to honor and respect those Indigenous peoples, their cultures and traditional ways of knowing, or multiple ways of knowing. And part of that, to me, is recognizing the kind of privilege that comes with Western education and Western research that supports things like this. And so making the commitment to, being cognizant of that and ensuring that I'm working with rights holders to develop research goals and making that a kind of a fundamental aspect of how I approach my research. So Christina gave my academic background, but I want to tell you and go back a little bit further and talk about when I became a biologist or when I decided I wanted to become a biologist. And the picture that you're about to see, I think probably maybe one or two people in this room has seen, and it's me without a beard. This is 18-year-old Sean, who started his undergraduate degree in biochemistry with, big plans to go into pharmaceuticals or something because, I liked biology and I liked chemistry in high school, but I had no idea what I wanted to do. And unlike, I think, a number of my colleagues, I never had this, affinity for reptiles and amphibians as a child. I didn't grow up specifically pursuing that. I love nature. I loved camping and hiking and all of those things. But to me, it was just being outside. It was being in nature. And I remember distinctly, I got the opportunity to go to James Bay between my first and second year of university on a project that was being run through the Royal Ontario Museum. And we were going up to look for yellow rails, which is a small nocturnal bird. So it was my first foray into reptiles, I guess. And the way our surveys worked is we would leave around 4 or 5 p.m., walk out into a salt marsh, have dinner at the end of our 5 or 6 kilometer transect, and then start as the sun started setting. And I remember walking through a salt marsh surrounded by mosquitoes and seeing this, what I can only describe as this kind of like Serengeti sunset, and thinking to myself, like, wow, this is a job. This is like something I like to do. And I could make this my career choice. And the best part of it was that by doing this, I would never have to do math again. That worked out really well. So a lot of my research has focused on how populations change and how they change in response to different levels of change, whether it be modifications to their habitat or the populations themselves. But I also am interested in how communities change and how those all interact within a landscape. So various species interactions, and especially how things can be affected when human land use changes come into play. And human land use changes are something that's, kind of ubiquitous throughout the planet at this point. There's very few places, if any, that have been untouched by humans. And whether it is things like agriculture or resource extraction or roads, or even just pollution, it really plays an integral role in how we understand ecology and how we have to approach conservation. So in my time doing this work, I've kind of reflected back on the work that I've done, and I've thought about kind of grouping my work into kind of 4 ideas or 4 kind of pillars that I think about how I approach my research. And the first one is that the assumptions that we make are gaps in our knowledge. And so I don't mean the statistical assumptions, that's a whole nother conversation. But I mean the assumptions that we make in order to do our science, the assumptions that we make about the ecology or the behavior or the comparability of 2 populations are all really important gaps in our knowledge that need explicit testing. The second is building a set of standardized tools or methodologies that can be used to increase the efficiency of conservation. Conservation has this problem where we don't always know exactly what we're going to do, and there's a lot of trial and error involved. But by using that trial and error to develop standardized tools, we can save people from going through that same process at a later date. The next step is evaluating conservation. And this one seems intuitive, right? We all want to know how effective our conservation initiatives or interventions are. But often this is a really challenging one, especially in terms of student or funding windows. A lot of my work has been on road ecology, which, ideally you have 5, 6, 10 years of data to kind of encompass a before and after and a slightly more after period to really evaluate how effective things are. But that's a really challenging thing to do. And so making sure that you follow through to the end is a really great thing to do. And then finally, what pulls all this together, and I really strongly believe that this is kind of a fundamental aspect of ensuring that conservation continues, is developing this network of grassroots stewardship. And this can be a combination of many things, whether it's Indigenous communities, rights holders, school groups, NGOs. There's all sorts of things that play into the conservation and making sure that it persists. So I'm going to go through a couple case examples to start. And the first one is something that most people in this room have probably heard something similar to, in that when we think about mitigating the effects of roads on turtles, it's adults that we really need to think about. They're the ones that have such high survivorship compared to juvenile cohorts. And because of that, focusing on adult cohorts when we think about road effect mitigation is really the solution. And I had a great student, Natasha Noble, up in the corner there, who challenged this kind of idea, and because we don't know enough about juvenile road mortality, really. And so she did all the kind of backbreaking labor of collecting dead on road juvenile turtles, dissecting them to identify the sex, and started this. And then it was kind of championed by Matt Keeble to kind of push it through to the end. And what we would expect is this. So if we look at the x-axis here, it's the life stage, so how old the turtle is. And on the y-axis is the reproductive value. And smaller turtles, or younger turtles, because of their survivorship being much lower, the amount they're going to contribute on average to a population is less. And that's what we expect given this kind of assumption that I'm describing. But looking at the number of turtles dying on the roads, what we found was actually much closer to this. So these black lines represent the actual total reproductive value of those cohorts. And we were finding that because there's so many juveniles getting hit on roads, the reproductive value of that cohort is almost the same as adult road mortality. And so when we target adult turtles, and not necessarily, often we'll have strategies that encompass multiple cohorts, But if we're not explicitly considering those younger cohorts, we could really be missing out on a large part of the conservation effectiveness that we're trying to reach. Another assumption is more of an implicit assumption that another great undergraduate student that I worked with, Rachel Dillon, who is here today, is that when we design road effect mitigation, we don't really consider the behavior too much when it comes to reptiles. Sometimes we'll think about whether or not they'll avoid tunnels, but in terms of mammalian road ecology, there's a lot more that has gone into understanding how animals use tunnels and the specifics about why and the behaviors they're eliciting while in the tunnel. And so we set up this arena, at a tunnel where a snake would be, oh boy, there we go, where a snake would be in the arena, and we would see how long it took to go into the tunnel and how long it would take to go through the tunnel. Our next step was we gave it the same snake. We gave it a second trial, but this time we gave it options. So it could go through the tunnel, but it could also go out either side. And we actually still had a majority of snakes go through the tunnel, which is promising as a start. But what we were really interested in knowing is whether or not these snakes were more effective at using the tunnel. And what we found is that even though they had more options, snakes that had been exposed to the tunnel already moved through the tunnel more quickly, kind of suggesting that maybe they are going to be using the tunnel more readily or more effectively. And just as a way of determining whether or not this change in our arena had some confounding effect, we ran another trial the following year with more naive snakes. And we found no difference between the two naive snake trials, but we did find that both of them took significantly longer than the snakes that had been exposed to it. The next assumption is another somewhat implicit one. And I think this is one that we often do think about in terms of how we design our survey protocols. But I think that it's a more complicated equation than often most people will give it credit. And so if you're driving by, or if you're surveying for reptiles along a road, you could do it by car, obviously not in the snow, but or you could do it by bike, or you could do it by foot. And I've done surveys in all three of these methods before. And so what we wanted to compare whether or not, there's a big difference between these two. And what we might expect is that there's this kind of just shift towards, a slightly lower relative abundance index versus the true abundance. So you might detect more, but it's probably a shift and it's probably a linear relationship. And I think often that's what gets built into these kind of models that allow us to correct for that. However, it might not be parallel. There might be some interaction effect that is occurring that is changing how we should be thinking about that. And to make it even more complicated, that effect might not even be linear. And so the first thing we did was we looked at whether or not there was a difference between the two methods. So between driving and walking, there's definitely a difference. You're going to detect more if you're on foot versus driving at 80 kilometers an hour. That's right in line with what we anticipated. There wasn't actually a difference, though, between cycling and walking the same transect. We were finding the same number of individuals, or the same relative abundance of reptile or of turtles along the road, given either method. And so this suggests that there's this trade-off between the amount of area you can cover and the amount of resources you have. And so if you need to cover a large area, the only thing you can do is use a vehicle, a car, but you can accomplish essentially the same thing on a bike as you could on foot while covering 3 times as much ground. The next step was another undergrad thesis that I collaborated with, and we were interested in how environmental variables or anthropogenic variables impacted how long a carcass would stay on the road. And so carcasses, animals, once they're hit by a vehicle, will remain on the road for some amount of time. They may be removed by a scavenger, they may be kind of bumped off the road by another car, or they could just degrade over time. And there's all of these weird things that play into it. But what we found was that there's actually a nonlinear effect of precipitation. So on the y-axis here is the hazard ratio. This is a metric that's used generally in life and death situations. It's a response to whether or not something is more likely to die or not. But we used it for removal versus persistence. And you can see above this dotted line is when a carcass is more likely to be removed from a road, and below that dotted line is when it becomes less likely to be removed from a road. And you can see it becomes increasingly more likely with that nonlinear reaction above about 4 millimeters of rain. And so when we think about our survey designs, often we'll say, we need to encapsulate rainy days and sunny days and warm days and hot days, but it's not just rainy versus sunny. It's the amount of rain that can actually influence this. And so, thinking about this in the early stages while you're building your models and building your protocols is a really helpful thing to kind of increase the effectiveness, or theoretically increase the effectiveness of what you're doing down the road. And then compounding all that, there's all of the seasonal variation and taxonomic variation that you see. And so depending on when you're surveying, you'll capture, a different thing if you're surveying, an adjacent site at a different part of the year. So it really does become this kind of complex question that needs to be addressed when you're designing protocols. So the next kind of theme that I want to talk about is this idea of building tools or standardized methods. And I think this is something that really chronically challenges conservation as a whole. Conservation often occurs across multiple scales with many, many partners involved. And so ensuring that it's almost impossible to have a cookie cutter version that we can just apply, but building towards those tools that we can apply in different situations is really powerful. And so imagine that as a wildlife manager, you've been tasked with conserving a population of turtles in this landscape. The first step that you would want to do is identify where those turtles are, identify what the threats are, and then you can kind of go about mitigating them. So actually, this is Presqu'île Provincial Park. This is where I did the majority of my PhD. And that's essentially what Presqu'île kind of approached us with. They were trying to identify where reptiles and amphibians were being struck on the road, and they wanted help developing a plan to mitigate and evaluate that intervention. And so we did a bunch of road surveys for about 6 years. After the 6 years, I think I had biked across Canada back and forth 3 times, which was weird to think back on, but a lot of fun. But in addition to those road surveys, I wanted to use a secondary method to kind of compare or test whether or not my road surveys were really capturing what was occurring. And so I chose to use landscape resistance modeling, which treats this landscape like a circuit board. So imagine that animals, or current, is flowing through this landscape, just like it's a circuit board, and areas that are challenging or problematic for those animals to move through have a high resistance, and the areas that are great for those species have a low resistance. And you can see that the color on this, the warmer colors would be areas of higher movement moving through. So this is a kind of a wetland complex. There's a swamp through here. And then those blue, cooler colors are where there would be less movement anticipated. And what we found comparing these two is that there was actually substantial overlap between the two methods for predicting where animals were crossing, which is great. It suggested that we were capturing it in both models. One thing that was quite a bit different, though, was the precision of the circuitscape model. So you'll see here this kind of large hotspot here is quite a bit wider than the hotspots we were identifying. We actually found about 3 hotspots in that small area given our road surveys. And so again, it's this trade-off between the amount of resources available for a conservation project and the outcomes that are, you're trying to accomplish. And if you have lots of resources, road surveys are great. They give you really precise estimates, but they do take a lot of time. Whereas, I said I did 6 years of road surveys. This model can be done in a few days. Once you have the data, it's just as simple as running it through the program. And so there is that trade-off. But one thing I think is really valuable is doing both of them and having that comparison, because when 2 methods agree on where a hotspot is, you have 2 lines of evidence suggesting that that is in fact an important spot. And Circuitscape will also theoretically help you capture those areas that have been historically very important, but whose populations have been depressed because of road mortality and you wouldn't capture in road mortality surveys. The next step is moving away from reptiles a little bit. So I hope you can excuse that. This is some of the stuff I worked on in Newfoundland, which was not the first project that I started working on and not the second project that I started working on, but it all kind of melded into something new because of COVID. There was this idea of investigating the relationship between occupancy and abundance. And so the question is, how can we more easily estimate abundance? And what's often done with game species or large mammals is we will survey a large landscape and we'll identify which of these cells are occupied. So whichever of those squares has a moose in them is considered occupied. And then you take that another step further, and you would resurvey a subset of these areas, and you would survey them much more intensively to get an abundance index that you can then extrapolate across the entire area. And so this is how a lot of game management occurs, usually from a helicopter, but also usually at like a 10-year interval because it's so incredibly expensive. And so there's ways that we can improve that, right? Every 10 years is not enough when you're trying to manage a population, to know, especially a population that you're setting harvest limits for on a yearly basis. And so one of the things I wanted to investigate was this relationship between occupancy and abundance. And so we're going to go through a little mental exercise just to kind of demonstrate how this relationship, which is one of the most, commonly supported macro-ecological relationships out there. Generally, there's this really strong, most of the time, linear relationship between the two. But when you scale down to a population level, which is the level that we're usually conserving on, you run into all sorts of problems. So we imagine a population of a gregarious species like wolves and a solitary species like moose, the same population size, immediately you're going to see that there's a different level of occupancy because of their distribution. And then if you change the scale of that, again, you have a different occupancy level because of their distribution. And so if we're interested in using occupancy data to generate abundance data or abundance estimates, this is a really critical thing that we need to consider that is often not considered. And what you get is these kind of odd relationships between occupancy and mean abundance or local abundance. But the important thing is by addressing these issues or explicitly building these issues into your occupancy abundance models, you can actually still accomplish the goal that you were trying to. And I used wolves and moose in this, but you could apply this to other species. So, a more gregarious species of turtle is a map turtle. After, we saw that in Greg's talk yesterday for sure, versus a snapping turtle that does not aggregate quite the same way and are much more territorial. So it's really powerful, but you need to be very careful when you're applying it. The next idea is this kind of pursuit of evaluating how effective your initiatives are. And so what we did in Presqu'île was we built this fencing along with this tunnel. There's 2 tunnels actually, but it was about 1.5 kilometers of fencing on 2 tunnels. And we set out to evaluate how effective both of those structures were. And so that's this kind of general approach to road ecology right now. The standard, best practice is you build fence to keep animals off the road and tunnels to facilitate connectivity, gene flow, things like that. And they vary drastically in size, right? So the picture on the right is fencing and tunnels that was built along Highway 69. That's quite a bit larger and has, different fencing infrastructure in place and so forth. And with our road surveys, we found that there was this steep drop in the number of turtles we were finding on the road, which is great. That was the core goal of what we were interested in. So in these 3 periods, so before mitigation, during mitigation was this is one of those weird kind of blips in a road ecology project where you think something is going to happen one way and then it gets pushed by 2 years because we need to check the hydrology and we need to do this extra survey. So we had 3 years before mitigation, 1 year where they were actively installing the fence, and then 2 years following mitigation. And one thing I want to draw attention to is the fact that there's no difference in the during year. Even though the fencing was partially erected, we didn't actually find any difference, which is supported by other research that's been done before that says, partial or poorly maintained fencing isn't really going to mitigate the threat. We found the same thing for amphibians. And although we did not really have a difference between our before and after period at our impact site, relative to our control site, which experienced a massive growth in the number of amphibians we were finding, this was still a significant response of mitigation. However, we did not find it was the same for snakes. And this was really interesting to me at first, but we reflected on some of the observations that we saw in the field, and we would often find snakes entering in the gaps between fence. So not gaps, that's the wrong word, but the way the fence worked was 2 long sheets of plastic, and they'd be overlapping with a 2-meter stretch. But snakes were seeming to permeate those without too much trouble. But I thought it was really interesting because not only were snakes permeating it, but snakes seemed to be staying in those kind of patches between the overlapping pieces of fence. And I think it would be interesting to follow up on this because, it was creating this warm refuge for a snake because it was black plastic, it would be warm, it would be a great place to gather energetic resources, but at the same time, there was no predator access to them at that point. So I don't know at a population level if the mitigation could still be having an effect because it's preventing predation, but it worked for turtles and amphibians. That would be a great follow-up. Wink, wink. So we also wanted to see if the tunnels were working as intended. And the first thing we wanted to do is to see if there was some sort of bias being introduced by the tunnels. This is especially important for either males and females or across species. But we found that regardless of the species, the sex, how far we captured turtles from the tunnel, the age and the size, none of these things were impacting who was using the tunnel. And we actually found between 5 and 45% of species that we had pit tagged, or of individuals from species that we had pit tagged were found using the tunnels. And that 5% bar is, a commonly used genetic bar for connectivity. So that's great. But the fact that, up to 45% of the garter snakes that we had pit tagged were using the tunnel really kind of hammered home that it was working well for them at least. And then the last little bit is something that I think herpetologists do a really good job at. This kind of idea of outreach and engagement. And I don't know if it's because all of our, focal species happen to be species at risk already, or if, just having a species or having an animal in hand is really kind of conducive to those outreach moments. Maybe it's some combination of those and other things, but it's something that I've noticed. But even just generally, as scientists, there's this drive to do outreach and engagement. But unlike a lot of the other science where we kind of iteratively change what we're doing so that we can have a more effective protocol or a more effective strategy, often we don't evaluate how effective our kind of ancillary outreach bits are, because they're not part of our direct project necessarily, but it's something that we should do, because often you'll have people that are very engaged and you'll have people that don't care at all what you're saying. So we tested this, and this was kind of more just like a passion project, really. I wanted to know if we were accomplishing what we were doing. I was doing outreach presentations to a group of grade 9 classes kind of around my study site. And so I went through the process of acquiring human research ethics approval, something I didn't really think I was ever going to do. And we asked them whether or not they were more likely to be participating in conservation. And we found that they were more likely, they were considering themselves more likely to help animals across the road, as well as take part in things like citizen science projects. And the biggest driver behind that was that they didn't know these things. So that's really promising, because often when we do outreach, we cite this, people don't know kind of fact, but this supports that. And something else that supported it was we found no difference between who presented these. So I took an extra step and we got 2 additional people with varying levels of herpetological or research experience to give the same presentations. And there was no effect of presenter on how likely people were to change their impressions. And this is just a kind of cumulative distribution word map. But I always, I really like the C presentation helps turtles. Is right there. And so the reviewers didn't really seem to like this way of displaying the data, but I always appreciate it. So I figured I would throw it in today. And so, taking those extra steps and kind of iteratively figuring out what works and what didn't work is a really powerful tool for outreach. And I know outreach is something that, like I said, is not necessarily part of our projects, but a lot of us do. But it really can have a, real conservation impact. And then finally, there's this second bit that remembering that developing partnerships is not an action, it's a process, and it's an ongoing process. Cool. And so this includes things like developing goals with your partners rather than approaching partners with goals that you have already set. Identifying those things is really useful to building those relationships. But importantly, if you want that conservation work to continue, again, we're dealing with academic or student or funding cycles, having the kind of community buy-in, whether it's an NGO or an Indigenous community or a group of school kids or just concerned citizens, really, really supports that work going on. And I know there's a lot of people in this room that build incredible relationships. I think that's incredible. But going about this is just something that we should all remind ourselves of when we're approaching this. And we can build on these ideas by sharing other things. So working to provide help with like grant writing or mentorship, education, reaching out to the community about the project, being part of the community or being engaged with the community rather than being the person who comes into a community to do work is a really important distinction. And then as well as that, kind of in-kind things such as training or sharing resources. And I think the sharing resources bit is a really tricky but important one. Giving communities the capacity to continue that research, it really gives them the ability to, take ownership of it. And I think that really supports this idea as well. So just kind of to recap, there's these 4 main ideas that I kind of group my work into. But generally, if we want to ensure that conservation is efficient and make sure it's as effective as possible, testing those assumptions explicitly and building them into our models, building some tools or methods that can be used and to support other conservation, making sure that we robustly evaluate our conservation, and then building that network that ties all of those things together are all really essential to ensuring that we can make sure that conservation continues. And lastly, I want to say there have been so many people that have been involved in these projects, many undergrads, many field techs, many volunteers, many communities, many mentors that, I can't list them all right now, but there's a lot of people who deserve a lot of credit for the work that I've shown you. And they've been incredible collaborators. But with that, I would love to take any questions.
So much of what you've had to say is about data.
Yeah.
And most data collection, well, could be better.
Yeah.
And clear that a number of the methodologies that are being developed and developed are to overcome the deficiencies in the data set.
Yeah.
So what would you recommend? Do you have any ideas? How can you collect better data?
Oof. Like in the context of road ecology or in the context of
Small, cryptic,
yeah.
and the advantage is not flying away.
Yeah.
They have their peculiarities.
Yeah, so I think it just goes back to kind of that idea of explicitly considering all of those little bits that you're building into your approach as you're developing it. Often, we're like, all right, we got the money, we got to go, we develop our protocol and we take from other sources. But taking that step back and really explicitly saying, how will this thing affect it? And how will this thing affect it? And a lot of those things might not actually be, important, but taking the time to consider those is a good kind of saving grace, I guess, to prevent those issues from arising down the road. Oh, yeah. So the question was, I'm working with the Conservation Authority. Someone is suggesting that there's often this push for more conservation at a larger scale, more outcome. And that's a great goal, right? But I think there's a couple of these things that can apply to that. So the circuitscape stuff, the circuit theory stuff is one of the really great tools. And you can use this across any size of landscape. There's a paper that just came out, I don't know, 6 months ago or so, that was the entire country. And, obviously it takes longer to run that model than just for Presqu'île Provincial Park. But that's a really great way to identify and cue in on important locations. And like with the Conservation Authority, like most of us, there's this strapped for cash feeling of trying to make your dollar go as far as possible. And so supporting road surveys or using road surveys to maybe augment those circuit models is a really powerful way to accomplish identifying movement corridors in a really quick and efficient way. The other bit was using that occupancy abundance relationship. If you can kind of explicitly consider how things will impact your model and measure that, then that model can be used across different scenarios within reason, obviously. But one of the things I'm looking at doing is taking that model, kind of developing or explicitly testing those things, and then applying it across the province to generate localized abundance estimates.